section, we're talking sequences and series. The goals, we want to find what's called the nth term of a sequence. That's goal number 1. Goal number 2, we want to write a series using summation notation. As a warm-up, I'm going to write down a list of numbers, and we call an ordered list of numbers a sequence, as you'll see. I want you to see if you can come up with the next number in the sequence. So the first 2 numbers are 1, the next number is 2, the next number is 3, and then 5, and then 8. Can you give me, see if you can write down the next couple of numbers, actually. Don't shout it out. Give everybody a chance to think about it. Okay, don't tell me what the overall solution is. Just tell me what the next number would be. 13. What's the next one? 21. Okay, what's the secret if you don't see it yet? Add the 2 previous numbers to get the next number, right? Yep. So what would the next one be? 34, and then what, 55, and then so on and so forth. Yep. This number actually has a name. Let's see if I can spell it right. It's called a Fibonacci. This number, I should have said this list of numbers, or this sequence has a name. It's called the Fibonacci sequence. There are many different instances in nature where the Fibonacci sequence crops up. You could just do a Google search, Fibonacci sequence, Fibonacci sequence in nature. And we'll just do images. And so it has some significance that you can see all these the spirals in these pictures. I'll talk about that in a second. It has significance there. But in simpler things, see if I can find the picture I'm looking for. I know it's here. There we go. So a pineapple. I don't know, what do you call the things on the side? I call them scales. The scales occur in a diagonal pattern, and if you count them, you'll get a Fibonacci number. Petals on daisies will often be, the number of petals will often be Fibonacci numbers. If you look, I just saw the picture here. The spiral you're talking, here's a good picture of it. Hard to see down here. But if you start attaching squares, first of all, of length 1 in this fashion, and then you get so notice these 2 squares have length 1 on the sides, and then this side created by both sides of the first 2 squares put together, that's a length 2. Make a square, put a square on that, then you've got a side of length 3 if you add the side of length 2 from the bottom square to the side of length 1 to the top square, and then you could attach a square to that, and then you've got a side of length 5 here, attach a square to that, and so on and so forth. The number of squares you get, or the lengths of the sides of the squares rather, will be Fibonacci numbers. And then if you draw the spiral as shown, you get a spiral that occurs in nature quite a bit, in a snail shell or a nautilus shell. And sunflowers, you can kind of see the spiral in there a little bit. And anyway, it's just an interesting sequence in that sense, that it coincides with things in nature. It's kind of mysterious that it does that. There's a formula for the Fibonacci sequence. If you don't mind the numbers depending on previous numbers, that is. It's not the kind of formula you're used to. It's actually called a recursive formula. So what we're going to do, we're going to let like F1, F subscript 1 stand for the first term in the list of numbers. F2 would be the second term in the list of numbers. Let's see, 1, 2, 3, 4, 5, 6. F6 would be equal to 8, and it would be the 6th. 8 is the 6th term. Does that notation make sense to you? So when I say Fn, what do you think I mean by that? F subscript n. What kind of number would n have to be? Positive, what else? Could it be like 1.2? It'd have to be a whole number, yeah. A counting number, really. We wouldn't even let 0 be there. Although you could technically start it at f subscript 0, and you'll see that with subsequences. But we won't do that here. We won't let it be 0 here. So fn, okay, that would be called the nth term, where n is just a number like n could be 100, 1,000, a million. N is some number, whole number. Okay, so this is the nth term. In terms of n, what would you call the number in the sequence, the term in the sequence that comes before fn? Like the term that comes before f6 would be what? Notationally? It is 5, but what would you call it with the f notation? F subscript 5, right? Which is really, somebody said it, f subscript 6 minus 1, right? So what would the term, using the f notation, the subscript notation, that comes before fn be in terms of, okay, there you go. That's what I'm looking for. I didn't say that very well, but you understood. Okay. So the term that comes before the nth term is represented by f sub n minus 1 because the nth term is represented by f sub n. Does that make sense? But that's not, this isn't true yet, is it, this formula? F sub n doesn't equal the term that comes before f sub n. But what do you do to that term? You add the term that comes before the term that comes before the nth term, right? Which would be denoted by f subscript n minus 2. And this is what we call a recursive formula. For fn, yeah, for f subscript n. But we just say fn usually. So this is called a recursive formula for fn. Now you guys are used to what I call plug and chug formulas. You want the output, you plug in an input and you run it through the formula and you get your output, right? That's not exactly what happens here. This is an easy formula to use, right? I mean, it's an easy concept. You add these two guys together and you get this guy, right? But what's the problem? What if I want f100? Which would be the 100th term. What do I have to find? I'd have to find the first 99 terms to get the 100th term, right? And that would be no fun, right? I mean, yeah, it would be, as somebody started to say what it is, it would be f99 plus f98. But in order to find f98, you need f97. In order to find f97, So recursive formulas are user-friendly, except they're time-intensive, aren't they? If you get big numbers. If you want the 1,000th term, well, just don't do it, right? It would take too long. But they're useful. And you have the notion of recursive formulas a lot in computer programming, which I might say more about later on, not today.